Hello, my name is MD Fazrabi Masumbillah, and I'll be presenting BLE Can See, a reinforcement learning approach for radio frequency based indoor occupancy detection. This is a joint work with my colleagues at the University of Virginia. It is estimated that in the US, residential homes and commercial office buildings are responsible for 39% of total energy consumption. About 70% of this consumed energy is used for lighting, heating, ventilation, and air conditioning systems, or LHVAC in short. These figures underline the necessity of the notion of energy-aware smart buildings. Research has found that a building occupant can increase a building's energy use by up to one-third of its design performance if they don't turn off their electronic devices while leaving the building. As such, we need a smart occupancy sensing technology that can control the HVAC system and electronic devices automatically. In addition to helping obtain energy savings, a smart sensing technology can control air quality, perform elderly monitoring, and building surveillance. There exist several occupancy sensing solutions, however, with various limitations. For example, motion sensors does not work when the occupant is not moving. Door sensors get confused when multiple people walk in the room in conjunctions or if there is a near door event. Carbon dioxide measurement based solution is slow since the level of carbon dioxide does not increase instantaneously with human presence. Installing cameras is not a viable solution as well, since cameras violate privacy. To overcome these challenges, in this work, we have focused on radio frequency based sensing solutions. The primary idea of the radio frequency based occupancy sensing scheme is that a person's presence can affect the radio signal parameters. Before going into detail how this works, let's see some of the typical RF signal parameters that are usually affected by human presence. Consider that in a room, a transmitter is transmitting a signal, and the signal gets reflected by a person or an object before a receiver captures it. Here, the time of flight is a radio frequency signal parameter, which means the time elapsed to propagate the signal from the transmitter to the receiver. RSSI is another popular RF parameter, which corresponds to the signal strength. Packet drop effect is an RF feature which occurs if an object or a person blocks the transmitter or the receiver. Now let's discuss the underlying mechanism of RF-based human sensing solution. Consider an empty room where a transmitter device sends signal to a receiver device in a continuous fashion, and the receiver receives either the direct signal or a reflected signal. The hypothesis is that if everything in that room remains unchanged, over the time, these received signals would build a silent profile. For instance, similar time of flight and similar RSSI. Now, when a person enters the room, she could create a noise profile by adding new multipath components caused by body reflection or altering existing multipath components. The idea is that with sufficient silent profile and noise profile, a supervised classification model could infer the occupancy of that room instantaneously. This RF signal dependent scheme overcomes the limitation of prior approaches. For instance, it can detect occupancy instantly, unlike carbon dioxide dependent system. It can perform regardless of human motion. It does not get confused in corner cases like near door event, and it does not violate occupant privacy. However, existing radio frequency dependent solutions has seen a slow acceptation by the research community for several reasons. First, the system requires a large database. For example, to identify human presence in all kinds of indoor environment, we'd need a huge database that basically would contain all kinds of occupied scenarios. Another limitation is that over time, performance of the scheme decreases in the room where it is initially calibrated. This happens due to the change of physical arrangements of objects in the room. The system fails to identify the new multipath component caused by a shifted object, for instance, here a chair, and it tends to characterize the reflection from the object as a reflection from a person. This means the system then starts treating the empty room as occupied. Particularly, this limitation is problematic as it means RF-based approach can only work in a stationary environment where the model is initially trained and would fail in a dynamic environment. One other limitation of this system is that this is very sensitive to radio placement. If we change the position of transmitter and receiver, which was used while collecting the data for training purpose, the pattern would be lost and the system would not work. We actually tested several existing RF-based schemes and saw that the performance of supervised machine learning models drops significantly in a 7-day period. As can be seen, initially these models performed very well since there was a little change in the environment. However, as days passed by, the performance degraded due to the object reorientation. To overcome the limitations of these existing occupancy sensing schemes, we have made two observations. Our first observation is that when a sensing scheme, say a motion sensor, makes a wrong prediction, human tends to react to this. Say he or she turns the smart TV or smart light back on when the motion sensor dependent control system turned off. However, since the motion sensor is naive, it does not learn from its mistake and makes the same error again. We focused on building an intelligent system that could learn from its mistake by observing this human reaction. Basically, it would take input from the smart devices which the occupant interacted with. Second, to adapt with the dynamic environment, we should be using a reinforcement learning algorithm instead of a supervised learning algorithm. Through continuous updates, this adaptive scheme would be able to retain high performance in a dynamic environment and can also predict the occupancy of a building which it hasn't experienced. This could also reduce the burden of labor-intensive offline training and large data collection. These observations helped us to come up with a model BLE can see or BLEX. BLEX makes three contributions. First of all, BLEX is an adaptive occupancy sensing technology, and it can retain high performance in dynamic environment. BLEX is scalable as it can predict the occupancy of a room which it has never experienced. And finally, unlike traditional Wi-Fi based schemes, BLEX extracts its radio frequency features from Bluetooth signals. This makes the system very energy efficient. Now I'm going to discuss the overview of the system. The center of the system is an RL application running inside a gateway of a room. Inside the room, we'd have some smart devices and sensors who can communicate with each other through Bluetooth. This communication can create some radio frequency features, which the RL application would receive wirelessly via a data processor module. Using this RF feature, the RL agent would decide whether the room is occupied or not. Based on the prediction, a control mechanism attached to the reinforcement learning agent would take a certain action, say turn off a light. A human could react to this action by turning it back on, which the RL agent would receive as a reward through the reward generation module. However, it might be an annoying experience if the agent keeps turning the light off. So alongside the action-based RL technique, we have also added an online learning feature where the agent would let the reward generator module know its decision without taking any action. Based on the feedback and the RL agent's decision, this module can generate reward. Implementation of the system involves three steps. First, the radio frequency feature generation. Second, feedback generation. And finally, the implementation of the RL agent itself. To generate radio frequency feature in a room, we deployed one Bluetooth-enabled receiver device and several transmitter devices. At the beginning of the process, the receiver device establishes wireless connection with each of the transmitter devices in a round-robin fashion and receive data packet from them one by one. Once a data packet is received, the receiver extracted radio frequency features from that packet. In our work, we have extracted three kinds of radio frequency features: time of flight, packet drop effect, and radio signal strength indicator, or RSSI. Now, let's see how we generated feedback from smart devices. With each electronic devices, we have attached a smart socket. These sockets basically monitor the power draw of the attached device and transmits it to the reward generator module. This module checks if the power draw of a device has risen from 0 or not. If it has, the module concludes that the room is occupied. In addition to the devices humans interact with, we have also taken feedback from nearby environmental sensors. The intuition is that if the level of carbon dioxide or humidity of a room does not change in a while, there is no human in that room. As such, if the level remains near constant for a certain amount of time, the rear generator module concludes that there is no one in the room. Finally, let's discuss the implementation of the RL agent itself. As you can see, the agent receives an input state from the environment, takes an action on the environment, and receives a reward for the action taken. Here, the dimension of the input state is R cross N cross K, where R is the number of features, K is the number of transmitter devices used, and N is the number of features concatenated. A common technique in RL algorithms is to stack consecutive samples and represent them as one state so that the state can contain temporal information. As such, we have concatenated 4 samples to represent as one state. The action space contains 2 types of action in our system. When the action is 0, it means the agent concluded that the room is unoccupied, and a control system attached to it can turn off the HVAC. When it is 1, the agent thinks the room is occupied. The reward function contains 3 types of output. First, when the agent and the feedback system agrees on the occupancy of the room, it gets a positive 1 reward. However, when the feedback system says the agent is wrong, it gets a negative reward. Finally, it can often happen that there is no feedback from the system. In this case, the agent gets no reward and the system stays stable. We have used a DQN algorithm to implement the RL agent. Due to time limitation, we are not discussing the algorithm here. However, it is discussed in detail in our paper. We have used 4 kinds of devices for prototyping. We have used Nordic NRI52 device, few Thunderbolt sensors as carbon dioxide sensors, and OSTAT smart socket as to provide the feedback. Also, you have used an NRI52 power profiler to measure the power requirement of the whole system. To evaluate the system, we created 5 benchmark models that use supervised learning solutions. For instance, PADS uses a SVM classifier to detect occupancy. Other benchmarks mentioned here also use supervised classifiers. As a ground truth, we used direct observation. To do that, we implemented a semi-automated system. Whenever someone was entering the room, they pressed a switch to notify the room is now occupied. While leaving, they pressed the switch again to notify that it's now unoccupied. We used F1 score to evaluate the performance of Blake's. F1 score is the harmonic mean of precision and recall. In our case, precision is how often the agent correctly predicts the room is occupied, whereas recall means the number of times the agent correctly identifies the room is occupied out of all occupied decisions. We tested our system in 4 different kinds of rooms, 5 different kinds of rooms, in 1 bedroom, 2 living rooms, and 2 office rooms. It involved up to 4 occupants. In bedroom and living rooms, we have tested the system for 7 days. However, in office room, we tested the system for 3 hours. While doing the evaluation, we tried to find answers to several questions, such as how does the system perform compared to the benchmark models? This figure shows that in a 7-day period, our system can achieve an average F1 score of more than 0.8 in all 5 rooms. Before the deployment, we actually trained the model in each room by collecting few hours worth of data. Compared to the baseline models, in the bedroom 1, the score is 7.48% higher. Here, Blake's is the system we implemented, and the rest 5 systems are benchmark system. We can see that in the living room 1, the score is 12.81% higher, and in living room 2, it is 6.6% higher. And finally, in office room, it is 2.22% higher. However, to truly understand the contribution of Blake's, we need to analyze the system's performance in later periods. This figure illustrates the performance of all competing methods in the bedroom in a 7-day period. We can see that as days passed by, unlike Blake's, performance of all the supervised classifier dependent models decreased. At day 7, the F1 score of Blake's is 0.21 more than the best performing model LSTM. This proves that Blake's is able to adapt itself with the changing environment and can retain a high performance, whereas competing methods fail. We have seen similar performance pattern in living rooms and office rooms. In all scenarios, our system outperformed other competing methods. We try to answer the question, can the system provide accurate result in unknown environment? To monitor the performance of the system in unknown environments, We initialize the IL agent with random network parameters before deployment. We can see that within 24 hours, the system is able to gain F1 score over 70% in all rooms. Finally, we also try to identify the overhead of the system. As can be seen, on average, Blake requires only 1.29 seconds to make one prediction, which means the system is instantaneous. On average, Blake requires only 6.74 minutes to update the learning model. We also monitored the power requirements. The receiver BLE node draws only 20.4 milliwatt power on average to collect data from all the transmitters. Each transmitter BLE draws less power, like 3 milliwatt on average, over one cycle of data collection. To summarize, in this work, we have developed a reinforcement learning dependent indoor occupancy sensing scheme. Our solution is easily deployable and adapts over time to changes in the environment. To operate the system, we require only 4 BLE-based devices, and it can be retrofitted in existing buildings. We have performed extensive evaluation of the system involving different indoor environments. We showed that our approach can achieve maximum 0.81 F1 score for occupancy detection in an unknown environment. However, there exist several limitations to our work, such as we compared carbon dioxide measurement of a room with a predefined threshold to provide feedback to the IL agent. In future, we want to incorporate advanced carbon dioxide-based occupancy detection techniques. Right now, our system can tell whether the room is occupied or not. We want to extend the system to support counting number of occupants in a room. Also, in future, we want to test the system in edge cases, such as multiple people entering or people walking through the doorway. With that, I'm concluding my talk. Thank you everyone for your attention.